Okay, hello again. We're on to the real series, lecture 14. The last time I lied, that was still 13, but this one is 14, the limit comparison test. And I do believe this is still 11.4 in the book. I believe so. And then for those of you just turning in, the book is Stewart Calculus, Late Transcendentals. Okay, so we talked about the comparison test last time. And that was just a straightforward comparison test. If I can say this series is definitely less than or equal to that series, then the convergence of the larger series implies the convergence of the smaller one, and the convergence of the divergence of the smaller series implies the divergence of the larger ones. But often you're comparing series that don't relate that nicely, but you can kind of tell they're similar series. They should converge. Basically, whether or not a positive term series is going to converge has a lot to do with how quickly the terms are going to zero. If they're going to zero fast enough, then it doesn't make it to infinity. If they're going to zero too slowly, then you might go off to infinity. The harmonic series, they're going to zero too slowly. But, the geometric series 1 over 2 to the n, that's going to zero fast enough that you actually converge to something. You don't go off to infinity. So, the idea of the limit comparison test is we're comparing how quickly these things are going to zero by taking their ratios. So in the limit comparison test, I've got two, again, positive terms. And just like with the comparison test and the integral test, we're assuming we've got positive term series. We'll deal with non-positive term series actually coming up very soon with alternating series test. But we've got two positive term series. And the idea is we're going to know whether or not one of them converges. And we want to, and if we can show that that limit as n goes to infinity of the ratio of the terms is equal to some non-zero, non-finite number. So it converges to some number, some finite number bigger than 0. Then we can say either both series converge or both series diverge. They're both doing the same thing. That means they're going to zero at basically the same rate if they converge to a non-zero finite number. So this first example, if you recall, this is one I tried to use the comparison test on before and failed because it wasn't, we wanted to compare it to the series 2 to the I over 3 to the I, which is a series which converges, but this is bigger than that, not smaller than that. So the straightforward comparison test won't work. But the limit comparison test will. If I take the limit as I goes to infinity of the ratio of these things, so 2 to the I over 3 to the I, it doesn't matter which one you choose, because if it converges to a non-zero, non-infinite number, then both the reciprocal and that will converge that. So this limit here is the limit I goes to infinity of when you invert and multiply, the 2 to the i's cancel and I get 3 to the I minus 1 over 3 to the I. And you can probably guesstimate that the 3 to the I takes over from the 1, or you can use L'Hopital's rule, or you can, in this case, separate. I'll just do that. Just to make it clear, I'll separate it into two fractions, 1 minus 1 over 3 to the I. And this 1 over 3 to the I goes to 0, so that whole limit is 1. The idea is that limit's not 0, it's not infinite, therefore this series here and this series here, both of these series do exactly the same thing. Since this series converges, this one must also converge. Okay, so since the ratio, the limit of the ratios was something besides 0 or infinite, the fact that this series converge implies that this other series must converge. Now, if this series diverge, that would imply this series diverge. They both do the same thing if that limit is non-zero and non-infinite. So now let's look at this next one over here. This next one's a little bit interesting. Looks rather complicated, doesn't it? Well, when you're trying to figure out what to compare it to, you really want to think about it in terms of limits. So I'm going to look at this as 5k squared plus 2. And remember, we're taking limits to infinity. And as I'm going to infinity, what's this going to behave like? Well, basically the k to the ninth takes over from the 3k plus 1, right? It really takes over. So this is going to be like, and the 5k squared takes over from the 2. That 2 becomes insignificant. So in infinite behavior, this is going to behave like this thing, because those other terms become irrelevant, which of course is equal to 5k squared over k cubed, which is equal to 5 over k. Okay, that tells me that probably I know whether this series converges or diverges. Can you tell me? It's 5 times the harmonic series, so it diverges. So the limit comparison test, I'm going to compare it to the harmonic series or 5 times the harmonic series. It doesn't really matter. I'm going to compare this to the harmonic series to see what's happening. So most of the work is in figuring out what it compares to, and that's basically the work involved in evaluating the limit. However, I do want you to show me that you evaluated the limit, that you understand what the test is saying. So I'm taking the limit as k goes to infinity of, let's do the harmonic series. Doesn't matter if we do the harmonic series or 5 times the harmonic series, they both diverge over this other series. And again, it doesn't matter whether you're looking at that or its reciprocal. So this simplifies to the limit k goes to infinity of, looks like invert and multiply, I get the cubed root of k to the ninth plus 3k plus 1 all over 5k cubed plus 2k. And again, as we're going to infinity, I'm not going to go through the proof of this, but this behaves like k cubed over 5k cubed. Actually, it behaves like the absolute value of k cubed over 5k cubed. But since it's positive, that is going to be a positive number. So that's going to be the same as the limit of k cubed over 5k cubed, because these other terms become insignificant. And what does that mean to us? Well, the k cubes cancel, and that limit's going to be 1/5, which of course is non-zero and finite. We knew we were going to get something like that. We sort of chose it to work that way, right? But anyway, what does that tell us? Since this diverges and the limit was non-zero and finite, this also diverges. Okay, this is a good place to stop.